So, take a second, go ahead and hit double-click that live button there you'll see on me. So you can, take a look at this wonderful syllabus that I'm sure you guys are very excited to go over. So, have fun. Alright, this is state law that I do have to go over this, so you get to bear with me. Okay, what do we have already going on here? Hopefully Kimberly's figured it out. Cool. Yep, I know. That would be crazy if she did. Okay, cool. Alrighty. Yeah, if you guys want to talk, go ahead and unmute yourselves. Otherwise, you can type stuff. I'm cool with either one. If you want to put your videos, go ahead. I'm not going to force you to do anything, so totally up to you guys. Alrighty, so, cool. Syllabus. Let's do it. Alright, so, hopefully you're all enrolled in Chem 106, OChem 2. Fun stuff. That's why we're here. I'm Alex Gluski. I'm going to be your instructor. There you can see there my email. Although you'll find that I am pretty much better at responding to Discord than I am to emails. Emails take a bit longer, and they tend to be a little more formal. Discord, go ahead and be as casual as you want. But if you want to email me, there it is. Office hours are going to be by appointment. Generally, again, if it's a quick question, just throw it in Discord in our general chat. I'll get it. It'll be pretty easy. If you want to get my attention, ping me by doing this. Something like that, where if you do at Professor G, throw your question there. That'll alert me so I can pay attention to you. That's kind of our best way. So, OChem 2, it's your second OChem course, of course. You can see kind of all the topics we're going to go over. We're going to start talking about ethers, the most exciting functional group of all, said no one ever. We're going to start with that, and we're going to go all the way through biomolecules towards the end of the semester. So yeah, fun stuff. You're going to cover things with Chalmers in the lab, such as spectroscopy, and I'm not quite sure how he's going to be doing the lab part of this, but I guess you'll be meeting with him tomorrow, so you can have fun with that. So on this course, we're going to be using Canvas and Discord. Canvas is going to be where all your exams and stuff are going to be, kind of more administrative stuff there, and Discord is going to be where we're going to be communicating and where I'll be kind of lecturing at you guys on Discord there, which is, I guess, where we are now. Cool. Blah, blah, blah. Yeah, you already know the days and times. Monday, Wednesday, 9-10. We'll be here. I do record all of our things that we do here, and I'll be posting them on YouTube. I'll put my YouTube channel in Canvas for you guys, so you can see. I also will put all my lecture notes in Discord here, so you guys can see those and work with them. I do have, for those of you who have had Chalmers before, for 105, for OChem 1, he did give me all of his, pre-filled lecture note things. If you guys find those useful, I can go ahead and put them up, but I'm probably not going to really be following them. But if you find that sort of thing useful, I do have those. I can put them up for you. So just let me know. Alright, textbook is the one by Wade, OChem. Not really required, so if you want an older one, go right ahead, save some money. Most of you probably already have one. Honestly, any OChem book will be just fine because they're going to cover the same material anyway. Just take a look at our kind of schedule of topics there to make sure that if you're using a different book that you're with the right chapter, because those chapters correspond with Wade. All right. If you somehow don't have models from 105 and you'd like some, there's the website for Darling models there. They're probably the most common ones that people use. They're super useful if you are if you can benefit from 3D manipulation of things. If you don't have models, I do suggest them, honestly, especially for when we talk about conjugated systems and Diels-Alder reactions. They're going to be super helpful for envisioning endo versus exo reactions. But we'll get there in a couple weeks. Grade-wise, looks like we're going to have exams, a final exam, and lab. That seems to be the way things are done here at GCC, so I'll just follow through with that. I may tweak those percentages towards the end of the semester to help you guys out. We'll see. But we'll talk about that in a little bit. Grade scale, standard 10% breakdown. I can mess with that as well if I feel like it, but it'll only help you if I do. And then you can see all of our fun, schedule of stuff. So I have it broken down by week. I've put important dates in bold there. So next week, no Monday class, it's Labor Day. And then your exams are there as well. Last week is going to be fun. You're going to have exam 4 on Monday, and then your final exam on Wednesday. Yay. That'll be fun. How exams are going to work is they'll be on Canvas. You will, if you can, print them out and write on them. If you can't print them, you'll just go ahead and take separate pages and you'll do your exam on those. It'll be open a little bit before class and a little bit after class time so that you have time to print it out, get ready, and then also to submit photos or PDFs onto Canvas. I'll have like a fake one up towards exam time so you can get used to making sure that your phone or whatever you're using to take the images works properly. Double check when you do submit them that it goes through. That seems to be a common problem, and then no one wants to have to deal with, well, it's 3 days later and I don't have an exam from you, and you took it but then I don't know that you took it, and that's a pain in the ass for everybody. So just make sure that things work out there. Makeup exams are not going to be available unless you have some sort of approval from me beforehand. So, and that's not like 20 minutes beforehand, So keep that in mind. Cool. And then there's some other stuff. If you have technological problems or whatever, let me know. I'll see if I can help. If you need accommodations through DSPS, there's our website there. And yeah, that's it. Any questions on syllabus stuff? Anything at all? Before we start talking about ethers. This is your one chance to delay me. So.
Professor, I have one question.
Sure, what's up?
Is the final cumulative?
Yes, it will be. And there will probably also be material from 105 on it. Which is really just unfair. I totally get it. But that is unfortunately the way that the ACS has decided to make the exams for OChem 2. And that's kind of something we have to do to make sure that your class is, like that it'll transfer properly, is by using the ACS finals. So unfortunately you don't have another option there. So you may want to kind of review a little bit of your OChem 1 material, especially towards the end of the semester. So just keep that in mind. That will be coming up. I will have a little bit of review time at the end of the semester where we can kind of go over stuff like that. But yeah, we'll see. Hopefully it won't be too bad. Any other questions?
Professor, go ahead.
Do you usually post like practice exams?
Yeah, I can give you some practice exams, yeah, for sure.
Thank you.
And the keys, yeah. I can steal both Chalmers's and Mrs. O's, so you can have extra fun stuff. In the meantime, my tablet is not behaving, so let's keep asking questions while I figure this stupid thing out. Was there someone else who had a question?
I was going to ask pretty much the same thing about a study guide, but are your tests, I saw you said it's like free response, all of it?
Yes. So they'll be as if you were in person. You'll be drawing your mechanisms, doing your arrow pushing, choosing your reactants, and all that fun stuff. So, yes.
Is it like typically 5 to 6 questions?
Oh, depends. Depends on how long they are, right? So, you'll typically get at least one mechanism question, so where you're drawing the arrows and each step of the reaction as it goes forward. You'll have a couple of fill in the reagents or fill in the product type of thing. You'll have some nomenclature stuff. And what else do we typically have there? Some synthesis as well. So, I mean, it's 4 questions minimum, I would say, but those would have, you know, separate parts within them. So, okay, so let's see. Let me learn how to restart my tablet because it's deciding to be a pain in the butt on the very first day. Yay. All right. Let's see. Any other questions in the meantime while we work on this? Ouch. Possibly a written question? No, that's another server. Okay. Aha! We have restarted it. A miracle. Okay, so give me a second to get that going, and then we'll start talking about ethers. So, hopefully those of you, it looks like we have a bunch of students from kind of all over, which is awesome. I'm assuming you guys have all left off after alcohols. So that's kind of where you should be. So when we start talking about ethers, that's taking into account that you've just finished alcohols beforehand. If not, you may want to just, you know, take a look at the textbook, you know, review your alcohol stuff, and so we'll go from there. Those of you who did take 105 last semester, though, just out of curiosity, does Chamras do, does he do like how to make that functional group first or how to react that functional group first? I'll try and keep it kind of similar to you guys. So we'll do nomenclature first for each functional group that we go through. But if you want to do, you know, reactions of ethers first versus how to make ethers, I'm cool with either way. So does anybody have any preference on that? Maybe? No? Okay. Then we shall do... Oh, I don't know. Do we want to just... Let's do, we'll do reactions first. Okay, so let me swap screens here to my tablet that is finally working. Ta-da! Alrighty. Ethers. Apparently we're starting with, like, forest green today. So, ethers and epoxides are going to be kind of our focus today and Wednesday. We'll also throw in thiols and thioethers later on if we have time, but this is going to be our first little bit here. Ethers follow the general format of something where you have an oxygen sandwiched between 2 R groups. Those R groups must be carbon-based. No H's allowed here. If you had H's, you'd have alcohols instead. Epoxides are going to be cyclic ethers, where you have a 3-membered ring here, and that 3-membered ring will be our epoxide right here. R can be H in this case, or other carbon. Either way. So hopefully that's not new stuff. Let's talk about naming ethers. We have a couple ways to do it. We have the common way, which is the probably most common. That's really helpful, I know. Common way of naming ethers is going to be you name the substituents in alphabetical order. We'll do plenty of examples. For example, here is an ether. If we want to take a look here, we have a methyl group and an ethyl group here. We'll want to put these in alphabetical order. This one will become ethyl, methyl, ether. Very exciting name for a very exciting functional group. let's throw the word ether as well in our definition there. Another example, you could have something like this. You'd want to look at your substituents. Here you have T-butyl. Here you have isopropyl. Remember that the T in T-butyl does not count for alphabetical purposes, so we just go straight for butyl. And so we are going to call this one T-butyl isopropyl ether. Is that not exciting? Is this not the most exciting functional group of all? Yeah, I get it. One more, perhaps, to make sure you can handle this. Alrighty. How about this one? What do we have on this nonsense? This side we have phenyl group, right? Benzene directly attached to the oxygen. Here we have a benzyl group. So this one will be alphabetical benzylphenol ether. Again, these are common names. So this is what you'd use, if you're, honestly, even with, writing papers and stuff, you'll use these names. People don't really use Iupac names for ethers. But also you'll probably have other stuff in there. And ethers, as you're going to see with the Iupac names, take very low priority in terms of naming. Alrighty, any questions on this very exciting way to name ethers? Alrighty. Moving on then, the Iupac method. One thing to note, ethers are substituents only. And what that means is there's not going to be a suffix for ethers. So if you remember your alcohol nomenclature, we ended something with OL, like butanol, or something like that, right? Where we had an OL at the end as a suffix. Ethers never will have a suffix because they actually have lower priority than alkanes in terms of naming. So we don't have to worry about deciding which group is more priority. They're lower than alkanes. They're really, really low. So how this works is you're going to have the kind of number of carbons, and then oxy will be your kind of way of doing this. For example, if we take a look at something like this, if we were to name this compound, we want to find the longest carbon chain, right? So we're going to see this is a 5-carbon chain, so that's pentane, right? And we're going to see on this we have an ether, right? It's got an oxygen sandwiched between 2 carbons. That's going to be a methoxy group. We have a methyl with an oxygen. We call it methoxy. So this would be 2-methoxypentane. And you'd still have all of your fun other rules that we're going to need to take. And so, in the style of teaching OChem, it only makes sense to do crazily complex molecules. So let's go ahead and do some. What functional groups have we talked about in 105? Really just alkenes and alkynes and alcohols, huh? So that's sad. Can't even do very much. Here's a fun molecule. Let's go ahead and figure out its name. as always, we love naming things, so if we are to do this, let's find our longest carbon chain and our highest priority group. So luckily for you, I've drawn our longest carbon chain right in the middle there. And we can see here we have got our highest priority group, the alcohol, on carbon 1. I'm making this easy for now. Nine carbons, meaning our parent name is going to be nonenal, right? We have nonane. If we wanted to be really crazy, we would say non and one all. I don't really ever like using the 1 there. If it's obviously on carbon 1, I would omit the 1, but if you want to be super precise, you'll keep the 1 there. And now we have a bunch of other substituents, and in fact we can't even leave it as this because we have a second alcohol, so we're going to need a diol in there too. We're going to see that this parent name is going to be nona-1,3-diol. Fun. Let's go ahead and look at what other substituents we have there. So we have our 2 alcohols covered. On carbon 5 we have, what do we have there? In terms of new stuff, what's our new functional group there? What is it? What's that name? What's this thing? What is it? Yes, no. Too shy, huh?
Ethoxy?
It's ethoxy, yes, very good. And we've got this boring chloro up here as well. Alright. Because I'm being mean, we're going to have to do some stereochemistry stuff. So on carbons 3, 5, and 6, we're going to have to take a look at Rns configurations here. So carbon 3, first priority is going to be our alcohol down there. We have an H, that's going to be our last priority in the back. If we look at the other 2, we have a carbon on each side, then another carbon. So these are the same, these are the same. We have another carbon. Let's look at what each other carbon has. Carbon 5 there has that ethoxy group. Carbon 1 has the alcohol. Remember, we always go in terms of atomic number. They're both oxygens that are on that. But the oxygen with the ethoxy group has carbon on it. The oxygen with an alcohol just has hydrogen. So we're going to see that the one towards carbon 5 there on the right side is going to be priority for being like number 2 for our stereochemistry. So we're going to have priority 1, priority 2, priority 3, which means that is going to be, what are we going to have there for our absolute configuration? Is that going to be R or S? Hopefully this is not something that you've thrown out of your brains already. It might be. What's this going to be?
Is it S?
It is indeed S. Very good. So we're doing a counterclockwise circle there from 1, 2, 3. We have our H in the back, or our 4th priority group in the back, so we can do this. And that's going to be there for S. If we do the next one on our carbon 5, we're going to see our first priority should be that ethoxy group, because that's an oxygen. The second group will be the carbon that contains a chlorine, and then the third one there. This is going to be an R as a result. Even though it is counterclockwise, we have our ethoxy group pointing backwards, so we need to do a switch. We need to switch it because we currently have our hydrogen pointing forward. To use this method, we need our higher priority group forward. We need our hydrogen in the back, so we have to flip the what we would get by doing this. So that's going to be an R. And then the last one, we're going to have priority 1 up here, priority 2 that way, priority 3 that way. This is going to be, no, I'm sorry, this is S as well. That is counterclockwise. No, yeah, counterclockwise. Yes, S. Counterclockwise, clockwise are hard, aren't they? Alright, let's do it. So, now that we have our parent name there, we have all of our substituents, we have that pain in the ass stereochemistry, we can go ahead and put those out there. So, we're going to put these in order. We have 3s, 5r, 6s. Now we must put our stuff in alphabetical order. So we have our alcohols taken care of already. That's going to be part of our parent name at the end, our suffix. With our substituents, we have chloro and ethoxy. Chloro has a higher alphabet kind of position, so we're going to have chloro. I'm sorry, we have, what is that, 6 chloro. I think this needs to be in parentheses, right? We have 6 chloro, 5 ethoxy, nona, 1, 3, diol. Fun. Nobody likes Iupac names, but for whatever reason we must learn them, even though these molecules are, like, you know, if you were to see this in an academic journal, people just put 1 by it, and they say compound 1, because nobody wants to spend all this time doing all this naming and stuff. But it is a skill that we're going to want to have for this course. So you may want to review your stereochemistry, you may want to review your kind of other naming rules for other functional groups. Alright, do we want to do another naming one? Or do we want to move on to epoxides instead for naming? So really all we're adding on with ethers is ethoxy, methoxy, isopropoxy, whatever random groups there. So that's the only new bit here. And those again are only substituents. They're never going to be your parent name for a compound. Alright. Very well then. Let's talk about epoxides a bit. So, with epoxides, or cyclic ethers, we have more naming rules. So, we can call something an epoxy group. Let's say this is our compound. We can name this as a substituent. We can name our epoxide as a substituent, and the substituent name for this would be epoxy. And how we would name this is we're going to name the 2 carbons that are part of the epoxide with numbers, and we're going to throw the word, epoxy there. So if we look our carbon chain, 4 carbons there, those will be how we're going to number them. So this compound would be 1, 2, epoxy butane, if we want to do it that way. So we just use the word epoxy, we put the 2 carbons that it's part of on there, and then continue naming as normal. I'm going to throw another one. Let's not make it as complicated as the last one. I'm not even going to worry about stereochemistry this time. Alright, so step 1, we're going to have to identify our longest chain. Again, because these ethers have low priority, we're not going to necessarily worry about, we're not going to have our chain be something like this. That doesn't make any sense. We're going to want to include something higher priority, which is going to be that bromine. So we're going to start from there. So we're going to have hexane will be our parent name here, since again alkyl halides are lower than alkanes. So we can go ahead and name these. On carbon 2 we have bromine. Remember, that's just bromo. On carbon 3 we're going to have isopropoxy. That's an isopropyl group on the oxygen, so isopropoxy. And then we're going to have an epoxy on carbons 4 and 5 there. And so with this, we're going to go ahead and put those in alphabetical order. Remember, iso does count for alphabetical order there, so that's going to be our third one. So to name this, we'll say 2-bromo, 4,5-epoxy, 3-isopropoxy, hexane. And there we have it. So, that is how we're going to name our ethers and epoxides. Sometimes, though, it'll be easier for you to name the epoxide as your parent, especially if you have more than a three-membered ring there. And so we have a bunch of unfortunate, as you'll see, parent names. Let's see, 5-membered ring, 6-membered ring. You're gonna hate these names. These all have names here that we're gonna want to load. This one is oxidane. This one is oxyrane. This one is oxolane. And this one is oxane. These are awful. But they are common enough that you might see these, especially the last one there. A very common solvent for chemistry is 1,4-dioxane. You can see it has that oxane name in it. And it's di because there's now 2 ethers as part of that. But these can be your parent names, so instead of, it's not going to be like cyclopentane or whatever, it's an oxolane. So if you have something like something like this, you would call it 2-chloro 3-methyl oxolane. Fun stuff. These names, I understand they sound absurdly similar to each other, right? Nothing I can do about that, unfortunately. So, yeah, fun. All they differ by is like 1 letter, 2 letters. That's it. So, you'll want to learn those as well. These can be parents of some sort of nomenclature fun exercise there. Alright? But that's how we're going to name cyclic ethers or epoxides. One last way you might see it, you might see something like this as ethylene oxide. That's a common name. You really don't see them for anything else, but you could. How those are named: they take the name of the alkene that would be where that epoxide is. So ethylene, 2 carbons as an alkene, and then you throw the word oxide at the end. So this could be cyclohexene oxide. That would be a common name for this. So it's the alkene name plus oxide. This one is not one I'll test you on, because they're less common to see these. But you might see this, somewhere in your careers. Though none of you are going into chemistry, you're all biologists, so you're never going to see this again. But it's still a good idea just in case. Ethylene oxide actually is one you'll see because it's very commonly used to sterilize equipment. So for sure that one is important there. But you see here, this comes from cyclohexene, and it's been oxidized by MCPBA or peroxyacetic acid, and now you have cyclohexene oxide. So it's just been oxidized. So that's where that name would come from. But again, not something I'm going to necessarily ask you to do. So you can dump this from your brains now if you like. Alrighty. Any questions on this naming business of ethers and epoxides before we actually start talking about real stuff? We good? Alrighty. Then let's talk about how to make ethers. We'll talk about epoxides later on, so we'll just focus on ethers right now that are non-cyclic. Really, what we want to take a look at when we're talking about making ethers, we have really two ways to make them. One is going to be just kind of acid catalyzed. Ether synthesis, and we also have one called the Williamson. The Williamson ether synthesis. We're going to see that the catalyzed one, acid catalyzed one, is going to be for symmetrical ethers only. And the Williamson can be used for symmetrical or for non-symmetrical ethers. Let's take a look at them, and we'll see kind of how this is going to work. So let's say I want to make diethyl ether. Or if we wanted to give it the Iupac name, it would be 1-ethoxyethane. Kind of awful name is that. Diethyl ether is a lot easier, but we'll put that out there. Just so we have some practice. We could have that as its name instead. But let's go back to this. We see that this ether is symmetrical, right? On both sides of the oxygen we have identical things. And so we can kind of take advantage of that fact in synthesis. How this will work is you're going to take the corresponding alcohol, throw it with some catalytic hydrogen, generally sulfuric acid. You'll probably heat this up to 135 or so Celsius, 150 Celsius. Really crank the temperature up. You're going to end up getting your ether, your symmetrical ether. And you'll get some water out as well as we do it. We're going to take a look at the mechanism. Hopefully you remember from 105, from Orgo 1, that if you have an acid-catalyzed process, the first step of your reaction is always going to be protonation, right? So, if we do that, let's just say we have H3O+. So sulfuric acid has donated a proton to some water. First step of any acid catalyzed process, you're going to protonate something. In doing so, we now have our protonated alcohol here. Our next step will be our second alcohol molecule will come in. And in nice SN2 fashion. Do you remember SN2, if necessary, will invert your stereochemistry? It is the substitution reaction, so we're having our alcohol come in and attack the carbon that holds on to that OH2 positive. Remember, water is going to be a great leaving group, right? You can't have OH as a leaving group, but water is a good leaving group. We're going to lose some water as a result. It's being kicked out. And then we're going to end up making protonated form of our ether. We've kicked out our water. You know what, in fact, let's make this a little bit easier to see. Let me do this alcohol in green, why not? So we have that there. And last step, as we recall, first step for an acid catalyzed process is always protonation. The last step is always going to be deprotonation. So here comes one of those friendly water molecules that we saw before. Like here we have one of them, here we have another one. One of those water molecules is going to come in. It's going to pluck off our hydrogen. We will have regenerated our acid. So the acid that we used here is regenerated, so hence it's catalytic. And we do lose one water molecule overall through this process. So it's going to work by protonation, substitution, protonation. All right. Questions on that one? Again, this is only ever used for symmetrical ethers, because if you tried to do it with asymmetric ethers, you're going to get a whole mess of things. You're going to have, if you try to mix two different alcohols together, you're going to get one that's maybe the first two alcohols, one that is the ideal product, and then one that's the last two alcohols. So only for symmetrical ethers here. So this is kind of one major way to make your diethyl ether, very common solvent. That's how you could do it. All right, not too difficult there. Standard catalytic process. Any questions on that one? Alrighty. We can just zip along here. We'll spend more time on the next one because it's a little bit more useful. We'll talk about the Williamson ether synthesis. And really this one, you'll be taking an alcohol and an alkyl halide, or really anything with a leaving group on it. And you'll end up getting your ether. Typically this is in the presence of a base. And so we're going to take a look at a couple of examples, and we'll look at the mechanism as well. So, this is again ideal for any type of ether. So if you want an asymmetric ether, this is going to be the way to make it. So for example, if we wanted to make this ethyl isopropyl ether, we could do that. we have a couple of options. We could say, okay, we're going to say we want this plus that. That would work. We could do it the other way around. Depends what you have. Either of these. Both of these would work. So you, in this case, for this ether, we can have either one be our alcohol. Either one can be our alkyl halide, or one with the leaving group. I'm going to say right now, though, this is going to be the better pathway if you want to make this particular ether, and we're going to look at the mechanism to see why. And the reason, I'll just tell you right now, is that this is going to proceed also through an SN2 type process. And remember that SN2 reactions happen best when your leaving group is on a primary carbon, right? So if it's on the isopropyl, that's a secondary carbon. It's a little bit harder for your nucleophile to get in the back there to go ahead and kick out your leaving group. So it'll be a little bit easier if you have your leaving group on a primary carbon. So let's take a look at that first example, where we have the isopropanol and the ethyl iodide. No, go away. So, first step here is if we go ahead and start with our alcohol. Step 1, we're going to throw in a base. Typically, the base you want for this is non-nucleophilic. So our handy-dandy best non-nucleophilic base is H-, typically from NaH or KH, hydride. Remember, non-nucleophilic base. Remember, if you did have a nucleophile there, you might end up messing up your ideal reaction. So you want a non-nucleophilic base for this. First step, you're going to go ahead and deprotonate. I guess I should draw this one sec. That's something like this. So you're going to go ahead, deprotonate. You're going to be left now with your deprotonated alcohol. You're going to lose hydrogen gas if you're using this base. That's why it's such a good base, because Le Chatelier's principle forces it to go to the right, because all that hydrogen just bubbles away, flies off into space. So that's how we're going to work with that. Now, remember that we have a localized negative charge here, which makes this a good nucleophile. Remember that alcohols are kind of not so great nucleophiles, right? They don't really have any interest in attacking things. They could, but it's just not very strong. Once we deprotonate, though, now we have a localized negative charge that's pretty unstable. So we're going to go ahead and have a much stronger nucleophile. It's going to be much more likely to react with something. And so what's going to happen is you're going to have your, what did we say, ethyl iodide? I guess I should do this in a different color as well so we can see. Here is our ethyl iodide. Remember, alkyl halides are going to be good electrophiles, right? We have that iodine withdrawing electron density from the carbon. Therefore, that carbon is slightly positive, makes it a good target for nucleophilic attack by this alkoxide. So here we go. Back to light blue for my arrows. It's going to attack that carbon, kick out the iodide. Again, this is kind of an SN2 type reaction, so if necessary, you'll invert your stereochemistry. We're going to lose our iodide through this. And poof, now we have our kind of product that we wanted. Here. I guess I should put this in green so that we have consistency. And if we want to put our lone pairs, there we have it. So again here, we're looking for, because this is an SN2 type reaction, we're looking for, ideally, our electrophile will be primary. So your electrophile being the alkyl halide, or whatever the leaving group happens to be. Halogens work well, but it could be, you know, if you've got a tosyl group or something similar to that, that'll work fine. But you'll have primary or secondary. Secondary is less kind of preferred. Primary is ideal. Tertiary, you're probably not going to have this react very well, unfortunately. And then you're definitely not going to have it with an aromatic situation, because remember, you can't substitute on sp2 hybridized carbons. It has to be sp3 stuff. And again, ideally, you're looking at primary or secondary. Your nucleophile can be any. Remember, that's your alcohol for this. All right, so these are kind of things we're looking for with Williamson. If we have something like this, what shall we do with this one? How about just methyl? If we wanted to make this compound, methylphenol ether. If we wanted to choose, we have option A, would be that pair of reagents. Option B would be this pair of reagents. Which of these do we think is going to be the better, the one that's going to give us our product here? What are we looking at?
B.
Yes.
I would say B.
I would absolutely agree with you. There's several reasons, in fact. One, you cannot substitute in an sp2 hybridized carbon, so the X on A there is not going to leave. You can't attack an sp2 carbon to kick out something. At least not yet. In 2 chapters we can, but not now. The methoxy would not be strong enough there, so to kick that out. But for right now, we haven't talked about that yet, so we're not going to mess with our benzene, so we can't kick that out. So yes, we're definitely going to have B there. Additionally, one thing, just so you remember, these guys are about 10 to the 5th more acidic than plain old alcohols due to resonance. So it's a lot easier to pluck off the H there with your base. So you can in fact use a weaker base. You can use sodium hydroxide on something like this to get it to react. So that's another reason that the kind of set of reagents there, B, is better. So not only is that first step, the deprotonation, going to be easier on you, so you can use a less hazardous base, but you also now have a primary leaving group on your methyl iodide or whatever that happens to be. So this is going to make this set of things really, really nice. So this is going to be the winner for sure. Part B. Definitely not this guy. You're not going to be able to kick out that leaving group there. All right. Let's do another one. Let's say I want yes, let's do this. Yeah, let's do this one. So with a little bit of stereochemistry in here. Alright, so with this, we're actually going to have a couple of options. But let's see, how can we make this? Well, first thing we can see here, it is not symmetrical, so we cannot just throw some acid in here and hope it's going to happen. So, we're going to want to use Williamson. With that, we see we do have some stereochemistry to keep in mind here. So if we're looking at this molecule, the Williamson, remember, makes that ether bond there. So we're looking at two components, two reagents here that are going to be on either side of that oxygen. So we have we can either have, I'm not going to put the stereochemistry on this one just yet because we're going to see it'll be opposite depending on what we want to do. Or, yeah, fine, we'll do it. We could have this, or we could have something like this. So remember, if we were to have something attack and have that X leave, whatever leaving group that is, if it's iodide or tosyl or whatever, if we want that guy to leave, it's going to flip the stereochemistry on us. So if we want us to end up with a wedge, if we want our alkyl halide to be the benzene thing, we're going to need that to be on a dash there, so that it's the opposite. But if we want our nucleophile to be there, we're going to want that on a wedge instead. So those are kind of our two options for the benzene half. And then if we want to look at the other one, we would then need... Actually, this one doesn't matter. It's not chiral, so... And then this one would just be isopropanol. Again, not chiral. So, with these, is there going to be a preference for one or the other? Probably not. These ones are probably pretty equal to each other. We're both going to have secondary leaving groups. But if we wanted to be really nitpicky, and I mean, this is just a very slight thing, probably that first set is going to be better. Just because, you know, the benzene is just slightly more bulky than a methyl group. So, if you were to kind of have a preference, either one of these I'd be okay with. If you were to give me either set of these reagents with some base in there, either one would work. They're pretty much equal, maybe a slight preference for the left one, just because that leaving group is in a slightly better, more accessible position. But either one there would be okay. Alright, so do we see how these kind of sets of reagents there could both work? And how they're about roughly equal? And how the stereochemistry works into play here? Let's use purple this time. So note here... don't forget here we're going to invert. I hate I couldn't fit that word there, darn. Inverted. So, if we want to look at that, if we want our product on a wedge, if we have our stereo or our chiral compound being the electrophile, we're going to need it on a dash instead, so that we're going to end up inverting our stereochemistry through the process to end up with the wedge that I asked for. But with this other one, because the wedges are nucleophile, we don't need to worry about it. So we're good there. All right. So really just two ways to make ethers. And they're both SN2. So exciting stuff. So either throw them with some acid and heat the crap out of them. You'll get symmetrical ethers out. Or you can do this Williamson, which is a more straightforward SN2. You deprotonate with a strong base, and then you'll end up using that as a nucleophile to kick out a leaving group on some electrophile. Alrighty. Any questions on those? Just so we're up to speed. X is a leaving group of some sort. Typically that will be iodide. Sorry, we don't need the negative there. Bromine. Chlorine less likely. Fluorine no. A tosyl group would be another example. What are some other common leaving groups? You could even have acetoxy. That would work as well. Something like that. So you need some sort of leaving group on it. Any of those would be fine. So that could work. So for example, let's say you only had, thankfully you're lucky and you have this chiral alcohol here. And let's say you've got isopropanol. Well, you've got some options here. How do we make this into our lovely product from before? Oh, I already was scribble on it, but if we wanted to do that, how might we do this? Oh, so far. How might we do this? Well, remember what we said last time, that our nucleophile stereochemistry is not going to change, our electrophiles will. So if we want that oxygen on a wedge in our product, we should probably use this as the nucleophile, and so we're going to need this one to be the electrophile. Nucleophile we can leave alone, we're just going to throw the base on that and it's going to become a nice strong nucleophile and it's going to do its job. But if we want that electrophile to have a leaving group, we're going to need to do something to it. So, standard way of making an alcohol into an electrophile could be, how might we do this? Remember, this is not a good electrophile. OH minus is actually nucleophilic. Meaning a terrible leaving group, not a good idea. So how might we turn that into something better?
Like the way we did before with the NaH, we can make it negative.
Okay, and if you do that, how is that going to make it into an electrophile? I mean, you can do stuff after that.
Oh.
Well, let's go with that. So let's deprotonate it. So we have now turned this guy into a nucleophile. If we want it to turn into an electrophile, what we might want to do is a couple of things, perhaps. Perhaps you remember way back when, this handy-dandy thing. This guy, perhaps? Also known as tosyl chloride, toluene sulfonyl chloride. Perhaps remembering this, it's going to really bounce up and then kick up the chlorine. Remember that OTS is an exceptional leaving group. It's very stable. So it's very happy to leave. So if we go ahead and now turn that isopropyl alcohol now into or just more simply that, now we have a leaving group on it. So was it Ramon? I think you said go ahead and deprotonate first. That would work.
That was me.
Yeah, so if we wanted to do that, we could, throw some base in there. Throw in some tosyl chloride. Again, that's this molecule here. This is TSCl. You end up getting now OTS, O-tosyl. Tosyl is a very good leaving group because it just resonates all over the place. Very stable. This is not good electrophile. This is a great electrophile. You don't have to use NaH for this. You could use a simpler base like pyridine, some other base. Just some base is enough. Just deprotonate that alcohol, throw in something to make it into a better electrophile. You could make it instead in acetyl group instead. You could throw in, instead of tosyl chloride, you could throw in acetic anhydride or acetyl chloride. You'll make it into a different type of leaving group. Either way is fine. So that's one way to do that. Did you guys cover this in 105? Maybe? Turning... You did, yeah?
We did, but we forgot it.
You did, but you forgot. Okay, as expected. So, alright. Well, then we'll just do... Okay. You could do it this way as well. If you did the same thing, take your deprotonated alcohol, you put in some acetic anhydride, bounces there, kicks off that. You now have this guy. Here, I'll make this a little bit more clear. I realize everything is the same color. Go away. I'm just going to go ahead and kick out the leaving group. I'm not going to bother with the... You haven't talked about carbonyl chemistry yet, so we'll forget that. Okay, anyways, doing this, aka... this is another way to turn an alcohol into a leaving group. So you'll want some base, deprotonate that alcohol, throw in acetic anhydride. Now you have, instead of an alcohol, you have an ester. And so, I mean, this is not going to be the best nucleophile or electrophile, but it could work. So tosyl is going to be your best bet. You could make it alternatively into one of these guys, but then you also run the risk of it attacking the carbonyl. So maybe that's not as good of a nucleophile or electrophile, but it's still better than the OH. So when in doubt, this is your way to go. So do something like this. Turn your alcohol... here, let me get the base in there. Turn your alcohol into an electrophile. Once you do, now you can go ahead and take your, whatever that thing was, the benzene with the alcohol. Now you can go ahead and do your reaction. So, first thing first, you've got to go ahead and convert this into an electrophile. So, if we're to take a look at this whole scheme again, let's just drag this down here, get it out of the way. Okay, if this was our question, if I wanted to take these, you're going to have to, first step, take your alcohol, throw it with some base, like pyridine, or NaH, or even NaOH would work for this. No, I wouldn't use an AOH. An AOH is a little bit nucleophilic, so let's not do that. And then you'll want to put in some tosyl chloride. Remember that tosyl chloride, toluene sulfonyl. That's this guy. It kicks it out, and you end up now with OTS. OTS is a leaving group. OH is not a leaving group. So once you've made it into OTS, now you're good to go. So now you can say, okay, we're going to take our alcohol here. That's one of our starting reagents. We're going to go ahead and put in some base. Second step, you're going to put in your electrophile. And lo and behold, now we end up with our happy product of interest, which was this random ether. And there we have it. All right, and so remember that OTS we generated in the last kind of little reaction here. All right, so hopefully this is somewhere stirring in the recesses of your brains, but perhaps not. So it may be a good idea to talk, or to review, go back to what, chapter 6 perhaps, I think that's where this is, to look at leaving groups and just refresh your mind there. If you already have it as an iodine, then you're good to go. You don't even have to worry about it anymore. If you really wanted to, you could go nuts and turn it into an alkene and then go ahead and throw an iodine on there instead, but that's a little bit more work than just tosylating, so fun. Alrighty. Any questions on that one? Where did we even start with this problem? That's the real question. Alright, so one of these pairs would work. Remember, if you want the stereochemistry on your electrophile, the one with the leaving group, the stereochemistry has to be the opposite of what you're going to look for in your product. All right. Any questions on that one? All right. We're going to do some more of that on Wednesday. I'll let it sit in your brains for a little bit, and then we'll do some more kind of synthesis problems with ethers. But let's just spend the last couple minutes now just asking this question. What do ethers do? What's the point of synthesizing them? Here is our answer. They don't really do much. There's one reaction we can do with ethers, and that is to break them apart. That's it. And so unfortunately, ethers don't really do very much. But that's not necessarily unfortunate, because we're going to see that their main use in industry, in chemistry, is as solvents. So, because they don't do anything, they make good solvents. So, because they're fairly unreactive, but they also have pretty low boiling points. So, as a result, when you're working with them, they can work as your solvent to help things find each other and react. And when you're done with the reaction, you just boil it away very easily, and you can isolate your product. So, ethers pretty much are just used as solvents. But let's take a look at what we can do with them. And that is throw a ton of strong acid at them. That's what we can do. Typically here we're looking at iodine or bromine. You don't really use hydrochloric acid for this. Hydroiodic or hydrobromic are better choices. We're going to see that when we take an ether, or more simply, like this, if we throw it with excess acid, some heat, what we end up getting is alkyl halides of both sides of that ether. And yeah, you'll get some water out as well. So that's what we can do. We can turn alkyl halides and alcohols into ethers, and then we can turn them back into alkyl halides. Yay. Very useful, as you can see. One thing to note, though, this process, just like before, is SN2. And so, if we have a sp2 hybridized ether, let's say we've got this guy. If we throw a ton of, if we put our excess hydroiodic acid in there, what we're actually going to get is this out. So just one thing to note, if you have an aromatic as one of your R groups, that one cannot be turned into the alkyl halide. It actually will become the alcohol. Yeah, we got a second to look at the mechanism here. Let's take a look at that first one. It'll be easier, and then we'll take a look at the second one. So, we're throwing in a bunch of hydroiodic acid, we'll say. Alright, let's look at this. I think that's what I had. Alrighty. First step, guess what? HI is an acid. We are going to protonate our ether. And remember, iodide is going to be a nucleophile, so let's take a look. We now have this positively charged ether bit here. And so, now, that's going to make it into a leaving group. And so, look who's going to come along, but our good friend the iodide that we just released from its H. Oh-ho. We're going to kick out our protonated alcohol. So now we have this little thing. If necessary, we would invert stereochem, because this is SN2. So if we had stereochemistry on there, we would invert it. We now have this thing. And because we have excess strong acid in here, we're going to do something very similar to before. Oh-ho. Light blue. So we now have protonated alcohol. I'm going to just draw this a little bit sideways if that's okay. And our iodide comes in, kicks it out. Oh dear. Okay, so this becomes, like I said, and so now we've, oh, I'm sorry, I need to be more consistent with my colors. Alright, we're kicking out our water, and lo and behold, we have our two products here, and we've made a water out of there. So, SN2, both steps, where your iodide's attacking, So you need excess acid for this to happen because we're not going to be regenerating our acid as we go through, so it's not catalytic. We need a lot of it. Not only is that acid going to be there to protonate our ether and alcohol later on, but it's also going to give us our nucleophile that we're going to kick out our waters with. And so as a result, we end up with both of them being alkyl halides, and we end up producing a little bit of water as well. We'll take a look at the aromatic example on, what day is it? On Wednesday. We'll do some more of this sort of thing. But essentially what you do is you just break it, you cleave your ether in half, and you stick your X on either side. Again, we're going to see, though, because it's SN2, you're not going to have this happening with aromatics. We're going to keep that as the alcohol. One last thing I want to point out, though. What I chose to, in this step, I chose for, in this bottom left step, I chose for the iodide to attack the left side first. The reason for that is because there's less steric hindrance in the way. Really, both sides are still going to end up with iodine on them, but technically the first one that should go is the less substituted side. So that's why I attack that side first. So if you were, if I were mean, which I can be, if I were to only give you one equivalent of HI in here, chances are you would just end up with the isopropanol. You would stop your reaction over here. That's what you'd end up with. If I were mean to give you one equivalent only. So just keep that in mind. Although you would still probably end up with a mess, you'd end up with both. But more likely than not, those are the two you'd end up with as your major products, with just one equivalent. But since we have excess, we're going to just keep on going. Everything's going to become an iodine through this. All right? Ooh, we did a lot. We did all of ethers today. That's how exciting they are. We were able to do it all in one, especially with going over this silly syllabus. So.
Professor, you'd never be mean to us, right? So you never give that question.
Mm-hmm. This is the only question you're going to get on your exam, in fact. So, have fun with that. No. Alrighty. Any questions on today's stuff? Just remember, I do post these, so you'll have this PDF here. Now that my tablet is behaving, you'll have this in our in our lecture notes channel here. So I'll share that right now, so you guys can have fun with this. Ta-da! So you'll have this there, and so there it is. Have fun. No, go away. And so, that's that. Any questions? We're going to continue on. We'll do a few more examples on Wednesday, and then we'll start talking about epoxides a bit. So, enjoy your day, everybody. Have fun. First day of class. For those of you who are on the wait list, go ahead and message me on Canvas so I can give you your ad codes, and we'll go from there. So, cutting the stream now. Cool. Any questions? Alrighty. If not, enjoy your day. Take care, everybody. And,
Bye, Professor.
Thank you.
And then to leave, don't forget to click the disconnecting in the bottom left.
Question.
Yeah, what's up?
Real quick. What chapters should we review from 105?
All of them.
Like, all of it?
Yeah, unfortunately. Though I would focus more on 6 and forward. So starting with substitution, elimination, and going forward from there.
Okay.
All right.
Thank you.
Okay, good luck.
Bye, Professor.
What's up? Oh, see ya.
If we server boost, can we get extra credit?
Get out of here.
Have I roll yet?
Go back to the stockroom, Eric. I think Goggeek is he's doing labs, so if you want to hear him talk and you can do this
Well,
stuff.
Why would I go there? He's just gonna for the entire